Swayam Prabha. Digital India. Educated India.
So last class I have discussed about the response of different conditions. So I have discussed the response of two cases, that is the undamped free vibration case and the damped free vibration case. Now today's class I will discuss about the response, how to get the response of few other cases. So for the first case that I will discuss today, that is actually the third case, that is our case 3, that is undamped force vibration case. So here the force vibration, that the loading pattern, it is the harmonic loading. I have already discussed and I have what is harmonic loading. Okay, so my equation will be, it is the undamped, so my equation will be m double dot plus ku, and that is equal to q0 into sine omega bar t. Okay, now where q0 is the amplitude of the harmonic load. Okay, and omega bar is the circular frequency at which the load is applied. Okay, so now the solution or the response I will get of this equation, or the response, so that is ut, sometimes I can write ut or u, both the same because it is a function of t. So that is equal to u0 dot minus omega 0 minus q0 beta divided by k 1 minus beta square, then that is into sine omega 0 t plus u0 cos omega 0 t plus q0 by k 1 minus beta square into sine omega bar into t. So what is beta? Beta is equal to omega bar divided by omega 0, that is tuning ratio. Okay, so now if I put u0 is equal to 0 and u0 dot, the initial displacement velocity, both are 0, then I will get qt is equal to q0 divided by k. q0 divided by k, because this is 0 and this one is also 0. So I will get by k, then this is 1 by 1 minus beta square, and that is equal to sine omega bar t, then minus, this will be beta sine omega 0 t. Okay, because we are putting this value 0, this one 0. So, but then if I simplify that, I will get this expression. Now, here I can write that q0 by k, that is equal to the static displacement, because static displacement or static force is equal to displacement into the stiffness. So, this is static. If I say this is static, then this term 1 by 1 minus beta square is called the magnification factor. So, which indicates that, so if I write that ut divided by u static, then it will be 1 minus 1 divided by 1 minus beta square. So, this is called the magnification factor. So, that means the displacement or the dynamic displacement is this value times of the static displacement. Okay. Now, this is our third case. So, I will get the response of the third case. Now, I will discuss about our fourth case. So, where this is the damped force vibration. That is also harmonic loading. Under harmonic loading. So, here the equation will be m double dot plus c u dot plus k u. So, it is all the terms are there. So, this will be q0 into sine omega bar into t. Now, solution or the response will be that ut, that is equal to e to the power minus damping ratio omega 0 t into cu1 sine omega dt plus c2 cos omega dt, then plus q0 by k 1 minus beta square by whole square plus 2 damping ratio beta whole square, then into 1 minus beta square into sine omega bar t minus 2 damping ratio beta into cos omega bar t. So, this is the solution. Now, this solution you can see that there is a complementary solution which is decaying with time. So, this is my complementary solution. Solution, it is decaying with time. So, this is actually is the transient response. Okay. Okay, and this is my this particular solution. So, that remains after the transient response dies out. So, this is called steady state response. Okay, so first part, this is your transient response, then second part is the steady state response. So this steady state response will remain after the transient response dries out. Okay, so now if I draw that part, the combination of this steady state response and the transient response. So this is my time and this is your ut. So that means initially this is your transient response which is decaying with time. So you can write, so that will basically decaying with time. Okay. Fine. And there is your steady state response will be like this. So this is steady state response, and there will be the total response. So this will be the total response. So this will be the total response. Like this, it will finish out. Clear? So I can write, this is my steady state response, or steady state, then this is transient, and this one is the total. Okay, green one is the total. So you can see that steady state response, that steady state part will remain after the transient part dies out. Okay. So now we have the two constants C1 and C2. How I will get these two constants? So these two constants C1 and C2 we can get by using the initial condition. Okay. So initial condition, you say that my at t equal to 0, that u0, ut will be u0, that ut that will be u0. Okay, so my ut will be u0 as t equal to 0, and u0 dot that will be also equal to 0 at t equal to 0. So these two boundary condition or two initial conditions we have considered. Now if I put these two initial conditions, then I will get C1 and C2 value. Then what will be the C1 value? C1 will be Q0 by K omega bar into omega d beta square minus 1 minus beta square whole square plus 2 damping ratio beta square, and my C2 will be equal to Q0 by K, then that is 2 damping ratio into beta 1 minus beta square whole square, then plus 2 damping ratio beta into square. Okay, so final response will be ut is equal to q0 by k 1 minus beta square by whole square plus 2 damping ratio beta whole square minus damping ratio omega 0 t, then this part is omega bar omega 0 beta square plus 2 damping ratio square minus 1 into sine omega dt, then plus 2 omega 2 damping ratio beta cos omega dt. So from where I am getting this, I am just putting the value of C1 and C2 in this equation. That's it. I am putting C1 and C2 because C1 I know, putting just C1 and C2, taking Q0 by K outside. Okay, other parts and Q0 by K and this term. So if you take this term outside, then thus this will be, this I can get from this equation. Okay, so but still some portion is there, the particular solution, steady state portion is there. So that will be q0 by k 1 divided by 1 minus beta square whole square plus 2 damping ratio beta whole square, then 1 minus beta square sine omega bar t minus 2 damping ratio beta cos omega bar t. So this is the total response that we will get. Okay. So now the steady state part. So this part, the steady state part, I can write this steady state part, I can write as ut equal to a sine omega bar t plus phi. I can write that. Now where a will be what? Where a will be, we know that this is q0, k is there, and there is a is a square plus b square, and this into this part. So this will be root over a square, means that will be 1 minus beta square whole square plus b square is 2 damping ratio beta whole square. Then here this is 1 minus beta square whole square plus 2 damping ratio beta whole square, because that we are writing a value here, because this part, and then root over a square plus b square, that we have already discussed. Now if you simplify that, finally you will get q0 by k into 1 by root over, because here you can take root into this within root, then I will get 1 minus beta square whole square plus 2 damping ratio beta whole square. And phi value will be tan inverse, then a by b. What is a? A is equal to your, this is a minus 2 damping ratio into beta 1 minus beta square. Okay. So similarly, I can see that here also I can write q0 by k is equal to u static. So if I write this u t by u static, then this part will be simple 1 minus this is your 1 minus root over 1 minus b square whole square plus 2 damping ratio beta whole square, and this term, because this is actually a part is there, so I can write this is also into sine omega bar t plus phi. So here this term again will be the magnification factor. So the magnification factor, if I say mf or f, that will be simple a by q0 by k. Okay, so that will be simple 1 root over 1 minus beta square plus 2 damping ratio beta whole square. So previous case this is my magnification factor 1 by 1 minus beta square. Here this one is the magnification factor. Okay, because this is your q static, so if I take this value here, or you can put the another way also, you can write that u by ut is equal to a sine omega bar t plus phi. So and u static is equal to q0 by k. So now the maximum value, if I write that u divided by u stat, ut by u stat, this will be simple a by q0 by k, and a value, you know, this is the a value, so q0 by k, that will cancel out, so this will be only the magnification factor. So this will be only the magnification factor. Okay, so this is our fourth case that I am discussed. Now the important one is the fifth case, that is the response under periodic loading. Okay, so till now we have discussed about the harmonic loading. Now it is periodic loading. So I have already discussed when I discussed the Fourier series that periodic loading can be approximated by a Fourier series as the sum of series of harmonic loading. Okay, so that we can express in terms of trigonometric form, and we can express in terms of complex form or exponential form. So first we will discuss the trigonometric form here, and then similarly we can express in the exponential form, but I will discuss about the trigonometric form only. So that means here the periodic loading is expressed by Fourier series, which is the summation of series of harmonic loading. Okay, so now if I put the trigonometric notation of form, then this load qt, that we can write a0 plus summation of n equal to 1 to infinity, the n number of harmonic loading. So summation of n number of harmonic load. So that is an cos omega nt plus bn sin omega nt. Okay, now here the Fourier coefficient are the similar way that we did in the previous classes or class. So that is a0 is 1 by tf 0 to tf into qt dt, which is the average over this time t to tf, 0 to tf, that I have discussed. Then an will be again 2 by tf, then 0 to tf, then this will be qt, then cos omega nt dt, and there will be bn, which is equal to 2 by tf, 0 to tf, then qt, then sine omega nt, then dt. Okay. Now here we can write that omega n, that is equal to 2 pi n by tf. Okay. Now that using the steady state part only, using the steady state portion only, then we can write that un into sine comma sine t, that is equal to, we can write by bn by k 1 by 1 minus bn square whole square plus 2 damping ratio bn whole square, then 1 minus bn whole square sine omega bar t minus 2 damping ratio beta n cos omega bar t. How I am getting that? Because this is the steady state part. You can see there I can put bn by k. Okay, here q0 by k, that is divided into an plus bn. So I am writing now, this is the sine t part. Okay, so I can write this is bn by k. Then you can see this term 1 minus b square plus 2 damping ratio beta whole square, then this part sine omega t minus omega bar t minus 2 damping ratio beta cos omega bar t. So that this way I am writing only this steady state portion, this equation. Similarly, I can write the un for cos t. So this will be, instead of bn, it will be an divided by k. Then this part will remain same, 1 minus bn square whole square plus 2 damping ratio bn whole square. Then 1 minus beta n square, this will be cos omega bar t, then plus 2 damping ratio beta n sine omega bar t. So this is the, we can write in this way. So finally the response u2 this ut, this will be u0 plus summation of n equal to 1 to infinity, then un comma sine t plus un comma cos t. Okay. Now if I write this equation, then the final form will be, if I write this equation, then the final form will be ut is equal to 1 by k. If I take 1 by k common, so this will be a0. Okay. So this will be a0 plus summation of n equal to 1 to infinity, then 1 by 1 minus beta n square whole square plus 2 damping ratio beta n whole square, then an 2 damping ratio beta n. If you simplify that, if you put and then simplify that, beta n, then plus bn 1 minus beta n whole square, then that is sine omega n t, then plus again an 1 minus beta n whole square minus beta n to damping ratio beta n, then that is into cos omega nt, that is whole bracket. Okay. So now you just put this equation here, u0 plus summation of this one. So you just put this ut sin t, un sin t and un cos t. So this is un sin t, un cos t, you put here and then you simplify that. You take this outside and summation of that and then simplify, you will get this equation. Just put these two equation here and then add them and then simplify it. You would get this equation, and then where you can write that u0 will be what? u0 is equal to here a0 we have read, and then we have written, and then there is a divided by k. So which is nothing but that is the static displacement. Okay, which is nothing but the static displacement. So this way we can get the response of a periodic loading by using the Fourier series, which is the summation of a series of harmonic loads. So I have discussed here only the trigonometric notation. Similarly, there is a exponential form is also there that I am not writing here. I have just written here the how to get the response under periodic loading also. So this is our fifth case. So there is only one more case remaining, that is the step loading. So the response how we will get for the step loading, that we will discuss in next class. Thank you.